In this video, we're going to go through how to multiply vectors. You've probably heard that there are two different ways of multiplying vectors. One is the dot product, and two, we have the cross product. Definitely don't get these two confused because they're very different. So when you use the dot product between vectors, I drew something. So the dot product is represented by a dot, and if we have two vectors, A and B, then we say A is dotted with B and we get a scalar quantity. We're going to see a lot of these in the first half of the course. When we move on to cross products in the latter half of the course, we're going to represent the cross product as basically a multiplication sign, a cross. And when we do that, we get a vector quantity. And in general, I do like to simplify how I think of dot versus cross products. Although I'll focus a lot more on dot products here in this video, I'm still going to give a little intro to cross products just so that we know what the differences are. Let's start our discussion by looking at two vectors A and B. So we're going to look at the dot product. And that means we must first define two vectors, A and B. So why don't we say A looks like this, and B is going to be here. So for the dot product, we are actually trying to find the projection of one vector onto another. So that means we must be able to compare the two vectors with each other if we're trying to multiply them. So instead of just looking at A and B separately, let's try to put them together where their tails both come from one origin point. So we need to understand that there is an angle, theta, between these vectors. So that means if I had my origin over here, I would have A coming out this way and B coming out this way. So essentially what I was trying to say before is the dot product resolves one of the vectors so that we're only considering the magnitudes of the vectors in one direction. So we have this angle theta over here, and a projection of A onto B basically means how much of A is going to be towards B. So the next step is to look at the dot product A dotted with B and B dotted with A so that we can find some relationships between the two. So let's look at A dotted with B and B dotted with A. So let's start with the first one, A dotted with B. It's pretty much the same as the drawing we had before, where we have A and B, some angle theta, and the fact that we're trying to figure out the projection of A onto B. So that means we do have a horizontal component of A that's in the same direction as B. So how do we calculate this AX? We know that cosine of theta is going to be adjacent over hypotenuse. So that means AX is going to be A cos theta, or simply A cos theta. So if we were to multiply the magnitudes of the two vectors, then we know A dotted with B is simply going to be A cos theta times B, or AB cos theta. Now let's look at the other example. We have B dotted with A, so we're going to redraw our diagram here with the two vectors. A was there, B was here, and we have an angle theta. So now it's a little bit different. We want to see what the projection of B onto A is. So that means how much of B is going to resolve into a component that is along A. So if we create a right angle triangle like this, then that means there's going to be a length here that's equal to, let's just say, BX. And we know that BX is going to be equal to the same thing. So we have the magnitude of B cos theta, because cosine of theta is equal to adjacent over hypotenuse. So now we have B dotted with A, and that's equal to the magnitude of B along the vector A, so B cos theta, times the magnitude of A, which is just A. And that gives us AB cos theta. So as you can see, these two are identical. So that means because A dotted with B is equal to B dotted with A, the dot product follows the commutative law or rule. So in other words, the dot product is commutative. Another thing to remember is the dot product is also distributive. So what this means is that if we introduce a third vector C, for example, if we have A dotted with B plus C, it means that you're multiplying A by an expression that's B plus C, and we can distribute A within that expression. So we can have AB plus AC. So that means we have A dotted with B plus A dotted with C. So apart from all this, the dot product is especially powerful when analyzing vectors. It can be used to calculate the magnitude of a vector, whether that vector is itself or another. So we're going to go through two examples just to show that. Example number 1. Let's determine the magnitude of just a random vector A. So if I actually wanted to figure out the magnitude of vector A, and I know that the dot product is simply the magnitudes of two vectors multiplied by cosine of theta, I can take advantage of the fact that cosine of 0 is equal to 1 and multiply the vector A by itself. So if I had vector A like this, could be any vector. If I multiply it by itself, then there's another vector A like this, and the angle between the two, theta, is equal to 0. So therefore, we have cosine of 0 being equal to 1, which means if I multiply A by itself, I'm going to get A cosine of theta. That gives me A squared times 1, which is simply A squared. Now let's go for another example. Determine the magnitude of vector C in the following. So we have A, and then we have B, and we have a third vector C going this way. Okay, so our job is to figure out what C is, the magnitude of C. So first steps first, how can we get to vector C using our existing vectors A and B? In order to actually figure out a value for our C vector, I need to be able to relate it back to the two other vectors in this triangle. So we can use tail-to-tail vector addition or subtraction and come up with an equation that relates all three vectors together. So in this diagram, A and B originate from some sort of origin O. What if we started with just A? So let's go this way. Let's just reorganize. We have A like this. Then we have vector B, but we could technically take the negative of vector B. So this is negative B. And that means from tail to tip, we have vector C. So technically we have A plus negative B being equal to C. So C is equal to A minus B. But now we want the magnitude of C. So from example 1, we know that we can multiply C by itself to get C squared. So we can use C dotted with C to get C squared cosine of 0, which is simply C squared. But there's something else that we also know. We know that C is equal to A minus B. So we have C squared being equal to A minus B. Well, let's just rewrite this so it's a little bit clearer. C squared is equal to C dotted with itself. So we can rewrite each vector C as A minus B. And because of the distributive law, I can now have C squared equals to A dotted with A minus 2B dotted with A plus B dotted with B. Okay. Now, we know that a dotted with a is going to be a squared. And we have minus 2. We know b dotted with a is going to be ba cosine of theta. And b dotted with b is equal to b squared. So now we have c squared equals to a squared plus b squared minus 2ab cos theta. And this is the cosine law. So we've just derived the cosine law, and you can see it's pretty simple if you understand how to use dot products and manipulate them. So what about cross products? So instead of looking at projections, we're now looking at the magnitude and direction of a vector that is at right angles to or orthogonal to both a and b. So for example, let's say we want a third vector that is orthogonal to both a and b. So let's find an a and let's write down a b. Then that means that c must be orthogonal, so orthogonal here and here, and that would be our vector c. And because of this and what we're trying to find, it must mean that if the cross product is going to be orthogonal to both a and b, it needs to have a direction. And because it has a direction, therefore a cross product produces a vector quantity. So I don't want to go into too much detail about this. I just want you to understand that when you use the dot product, you actually get a scalar quantity, so you get some number or magnitude. But when we move on to the cross product later on in the term, you're going to have to understand that it has both magnitude and a direction that you have to consider.